All right, this is going to be lecture 2, and this is all still in the same day. So getting a little weary here, but this one shouldn't take too awfully long. But it's one of the more important things that we do. So, and most of it is going to be just kind of off the slides, and I hate to do that to you, but it's just kind of the way you got to visualize electric fields. Then we'll look at your homework problems from it. All right. So this one may not be as hopefully as long as the last one, but remember when you're first getting introduced to something, it takes a while to get it all set up and ready to go, and then on in 2 days, which is unbeknownst to you, you'll just see it all as one thing. You'll get lecture 3, which covers what we call electric potential difference, all the same thing, which is not electric potential energy, by the way, but it's all wrapped up together. Um, so here we go. Let's just go ahead and let's put this slide on slideshow, set up the slideshow the way I like it. Okay, there we go. So let's just play it from the current slide. For some reason, it's keeping it. So this is good. All right, so here we put a test. Now look, a small amount of positive charge here, large amount of negative charge here. And let's put a test should have a small magnitude so it doesn't affect the other charge. All right, so here we've got an ebonite rod right here, okay? The positive charge experiences a force, which is the vector, so it's got a negative force here, negative force here. This is a positive charge, all right? It didn't say it's negative, so it's positive charge. It's going to be attracted to these negative charges here, and it's going to be getting pushed this way. So it feels a force going this way. And there's pretty much saying that this ebonite rod, since it's closer to it and has fewer negative charges, is since this one has more negative charge but it's further away, it'll have a negating force. In other words, it'd be attracted here the same as it's attracted here. So it's going to go in a straight line this way. All right. Now here's the deal. The positive test charge has a magnitude of 3 times 10 to the 8 coulombs and experiences a force of 6.0 times 10 to the negative 8 newtons. Find the force per coulomb, F over Q naught, that the test charge, predict the force that a charge of 12, positive 12 coulombs would experience if it was replaced the test charge. So here we go. We wind up with this 6 divided by 3, all right? And notice the 10 to the 8s disappear. And we wind up with 2 newtons per coulomb. That's the units for an electric field. All right, so I'm going to put that on my notes right here. I'm going to let you know that, so this is for lecture 2. So the units for the electric field are newtons per coulomb, all right? And we already saw that it is the force divided by that little charge that's out, the charge that we're trying to figure out. What is the electric field on that charge? And that is equal to E. Because this is a vector, and that's a nice, and charge coulombs, of course, is a scalar. I don't know why I said of course. If you're brand new to this, you wouldn't know that, but it's a scalar because charge is analogous to mass. Because look, the force that it feels is equal to Q times E. Oh my goodness. Then there's another, so if it's Q times E, well, what did we say E was before? If it's Q times E and it's feeling a force, then that's the same thing as K times Q times some Q, which is making up that E, divided by R squared. All those charges making up divided by R squared, because that's what Coulomb's law says. If I divide that, then I wind up with E is equal to the electric constant times the sum of all those charges. What are all those charges and their distance away from that test charge? So here's equation 2, here's equation 1 for the electric field, okay? And that's what you're going to see in these next few slides here, Okay. All right, the electric, there you go. Newtons per coulomb. We're also going to see later on in chapter 16 this volts per meter too. Okay. The electric field that exists at a point is the electrostatic force experienced by a small test charge placed in that point divided by the charge itself. A field is something where an object feels a force. That's what a field is, a gravitational field, an electric field. Okay. Now notice, if I put a positive charge here, it's going to go in the direction of the electric field. A negative charge, this is what's weird, because we're not used to dropping things and have them go up in the gravitational field. But they would go up if the sun was a lot closer and had a much greater gravitational field than the Earth, and we got around by suction cups. All right, but anyway, we're not used to things we're not used to things going in the opposite direction of the field because we're so used to the gravitational field pointing towards the center of the Earth. That's all we did in physics 1. But now in physics 2, we've got this electric field pointing in the opposite direction. So the charges on the two metals in the ebonite rod create an electric field at the spot indicated of 2 newtons per coulomb. Determine the force on the charges A and B. Okay, well, it says F is equal to Q times E. So that's positive, and that would be negative. So this would be positive 36 times 10 to the negative 8 newtons. Notice you get newtons per coulomb, all right, times coulomb, so the coulombs cancel. This would be negative 48 newtons because the coulombs cancel, all right? It's the electric field. It's also a vector, and you can add it up, but I like to do, remember, we've got too much to do, and this is too difficult of subject to be messing with 2 dimensions. We'll let the engineers mess with that. You guys are future doctors and things, and dentists and pharmacists and or geologists. You've got bigger fish to fry. All right? So here we go. The electric field of a point charge. So here's my little point charge. Here's big Q. The isolated point charge of 15 microcoulombs, Q naught, is in a vacuum. The test charge is okay, so here's an isolated point charge. It's in a vacuum, so in other words, it's feeling no forces on it. It's just stuck there. We've glued it down. The test charge of 0.2 meters away is to the right, and it is 15 microcoulombs. Well, here E is equal to F over Q. Determine the electric field at point P. Okay, well, I know that F is equal to K times Q1 over Q2 times R squared, so I can figure that. Get 2.7 newtons. And then F divided by Q naught, notice I get newtons per coulomb again, which is the direction of my electric field. Okay, let's stop here and take a look at maybe, and then we'll come back and we'll look at some of that little ICP quiz, which is only 4 questions this time. I kind of went nuts. I was like, why am I killing myself?